Good morning, good afternoon, good evening, depending on where you're joining us from today. This is Mike Mazzarese with AST Environmental. Thank you very much for joining us in this. This is our second webinar in this series that's really focusing on individual projects, so kind of like a platform presentation that we've seen in conferences. Obviously, we're not going to conferences these days. Hopefully soon. But as the host at AST Environmental, I just want to thank a few folks, RPI, founders of the RPI Group. So RPI Group is a consortium of companies that apply what we call the RPI trap and treat approach. Our European partner in our group is Ejlskov, and today Giorgio Ceriani from Ejlskov is going to present on this particular project. It is a confidential location, so we've just classified or listed it as European industrial site. And so I know some folks, this is late, especially if you're in Europe and you're joining us. For some reason, you have to jump off. This is going to be recorded, and this will be placed on the RPI as well as the AST websites. Some of the content today is going to be expanded upon in our next webinar, which is next month, which is going to focus on what we call the qHRSC method, or the quantitative high resolution site characterization method. Brings together high density quantitative sampling, so soil and groundwater, with modeling and maybe integrating high-res characterization tools like, say, the MIP and the UVOS. And Giorgio is going to touch a little bit on that in this presentation. It was integrated into this approach. Lastly, before we get started, if you do have any questions today, you'll see on your little slide bar on the right, we're all experts now on webinars. Go ahead and put those in the questions question drop-down menu there, and we'll go ahead and everyone will be muted until we get to the end, and then then I will jump back on and we'll go ahead and address those questions. So with that, Giorgio, the floor is yours.
Thank you, Mike, and likewise, good morning, good afternoon, and good evening to everybody joining today's webinar. What we would like to present today is a case study out of a site where we have been working now since we started in 2016 throughout site activities and monitoring. We are now at 5 years into this project, and we would like to focus on kind of like more data presentation and what we have been done and the whole approach that has been put in place for this project. As Mike mentioned, the site is confidential, so we cannot really disclose critical information, but as mentioned, we will try to focus on the data and what has been done. So a little bit of history about our site. The facility has been a dry cleaning and repair shop since the 1960s. And throughout the years, it has been going through a series of site investigation which have highlighted the issues of chlorinated solvent contamination, both in soil and groundwater. This led to a series of activities on site, combined to some site infrastructure refurbishment, starting in 2003 and 2004, where excavation remediation was performed in between the two buildings where the former USTs for the PCE were located. At the same time, an air and biosparging system was launched and run in the basement of the building for a few years, alongside a pump and treat system with a extraction well located downstream of the building, with the aim of trying to create a sort of hydraulic containment for the plume, which had been migrating off-site and over the years had caused some issues to some of the, let's say, private house owners located downstream of the site, which were forced at some point to discontinue their pumping wells in their own houses. So what happened next to this site was that in 2015, Ejlskov was brought into the project and was asked to sort of try to provide an end-to-end plan, which with the aim of trying to bring the site to a closure in terms of monitoring and remediation activities as such. The end-to-end plan started from a sort of site review of the available data, both historical investigation, what had been done so far in terms of remediation activities, and with that data try to evaluate where any data gap were still present in the conceptual site model by trying to identify them, conducting what we call a remedial design characterization, which is a pre-remediation activity which the RPI group has specialized over the years in trying to define the real issue in terms of soil and groundwater contamination at the site, allowing us to refine the final remediation plan whilst also defining final remediation criteria. The remedial design characterization leads to what we do in terms of active remediation, and the advantages that with the additional data that we gather during the RDC, we are able to ensure that we can provide a more, let's say, surgical approach to the remediation, hence using the remediation budget in a more efficient way. Following the remediation activities, we are then able to continue the performance monitoring of the remediation by conducting normally only groundwater monitoring, but in some cases we are also asked to conduct soil validation activities to compare baseline values against the ongoing performance data from the monitoring activities. For this specific site, the approach of the RDC was performed by doing, as a first step, a site-wide MIP investigation. As we can see from this map, the total amount of MIP points conducted at this site was 45 points, which covered an area of approximately 60,000 to 70,000 square meters. And the aim of the MIP investigation was, in a way, a double activity. We had to sort of make sure that we could locate any unknown source area which was not yet found at the site, and at the same time try to identify in the downstream area the sort of flux zones based on the bedrock depth present on site. What we then followed up after the MIP was a soil coring activity which covered the most, let's say, contaminated areas which were found with the MIP investigation, where we collected a total of 255 soil samples across a number of locations. What the RDC investigation highlighted already during the site activities was that a new source area was found in an area where also the client was not aware of that, which compared to the, let's say, previously thought being source area in between the buildings, was actually located north of the building, where a large area affected by DNAPL was discovered. The RDC works included also groundwater wells installation, and with all this data combined, we were able to refine the conceptual site model to how shown in this slide, where we can see that the source zone is located within a layer, fortunately for the client, where some silts and clay was present, and that layer allowed the DNAPL to remain trapped within the first 6 meters of the portion. This source zone, though, caused a large plume to kind of develop in the primary aquifer located on top of the bedrock, and to spread, as discussed initially, far downstream of the site boundary. What the RDC, as we discussed, allows us to do is to truly understand in detail where the problem is. As we can see from this slide, we have kind of cut in slices the soil and MIP data that we collected during the RDC. And as we can see, the problem was truly located in a, let's say, at this scale, small portion of the site, but within 4 to 6 meters. Above and below, we can see that the soil contamination sort of disappears, and the rest was, again, a large plume of PCE originating from this source area. In this slide, we are now summarizing the RDC results in soil, groundwater, and how this data allowed us to generate a new remedial plan for the client compared to what the original plan was at the time Ejlskov was brought into the project. So as we can see in the upper corner on the left, the soil data show us again how concentrated, let's say, the soil mass was at the site in a specific area, whereas the plume originating from this source zone was covering the whole site, the whole portion of the property that was investigated, and also spreading further downstream. The site, in terms of remediation, was then split in 5 sub-areas, which were kind of both assigned a different injection profile in terms of amount of product to be used and injected. And as we can see from this interpolation of the soil and MIP data, the estimated contaminant mass in all the different sub-areas was quite different. Area A and B are 2 areas located in this top portion of the property, and as we can see, the most of the amount of the PCE mass was located right there. Area C and area D are located in between the building and in the basement, where some residual mass was also found. And finally, a small area outside of, let's say, of the main portion of the site was also identified, and it seems that this area was used probably back in the days as a sort of, like, let's say, waste garbage area, but nothing significant in terms of like true source. The reason why we have highlighted this sort of L-shaped areas, because as we discussed, the original plan for the site when Ejlskov was brought in at the site was to sort of possibly install a permeable reactive barrier at the site boundary, because the main, let's say, objective of the remediation was to try to cut off the plume from exiting the site to a specific concentration. Once the RDC was completed, though, and we realized how concentrated the soil mass was, we kind of revised the approach and discussed with the client the opportunity to actually target much more actively the source and try to sort of, let's say, cut the head of the snake and then work indirectly on the plume. And this was done at the end of the day when in 2017 Ejlskov completed the injection works with a total of 702 points and the installation of roughly 52,000 kilograms of Cat 100, of which 3,800 kilograms were BOS 100 only. Here is just a couple of pictures to show the site activities. The one that we like, let's say, most is the one showing the activities in the basement of the site. We have been performing roughly, I think it was 160 to 170 injection points in a basement with less than 2.1 meter or 7 feet clearance. We custom build injection rods able to kind of work in such condition, and sort of slightly change the standard mini rig that MT540 that GeoProbe provides for this kind of activities. The 2 technologies used for the project, for those that may be familiar, it could be just a refresher for those that are new to the 2 technologies. The site was, as discussed, mostly done with Cat 100, but Cat 100 is built upon let's say the technology called BOS 100, which is an abiotic in situ technology used to degrade chlorinated solvents. What is BOS 100? BOS 100 is simply granulated activated carbon, which is initially soaked with a ZVI salt solution and then cooked to temperatures up to 800 to 900 degrees Celsius, which allows the ZVI to become embedded within the porous structure of the granulated activated carbon. What this does to the activated carbon is that it creates a new product on its own. So we're not dealing anymore with activated carbon or ZVI, but it's a truly unique product where the characteristics and the properties of the activated carbon are combined together with the properties of the ZVI. So what happens in reality when we use this technology? The contaminants that are traveling together with the groundwater flux becomes absorbed to the activated carbon to the maximum capacity that the carbon has. What happens next is that the fact that the ZVI is embedded within the carbon structure allows the mother products such as PCE and TCE to degrade completely to the end products, non-toxic end products like acetylene and ethylene and so forth and so on. And this concept becomes, it's a continuous trap and treat effect until either all the contamination is completely taken care of, or eventually at some point you may end up running out of ZVI. And that is the importance of conducting the RDC, meaning that we don't want to run out of ZVI. Else what will happen is that you are left only with granulated activated carbon, which will have a absorption capacity to a certain point, but will not allow any degradation ongoing. So to fight this issue in this site where we had DNAPL concentrations in soil and groundwater, the upgrade of the BOS 100 technology was introduced for the full-scale treatment, and this is CAT 100. What CAT 100 does is that introduce a biological treatment of the chlorinated solvents by mixing BOS 100 alongside an electron donor source, being generally starch, and facultative bacteria naturally occurring, which are mixed together with the slurry prior to the injection process. What happens with this when this technology is used is that now the ZVI doesn't become anymore a limitation, because we are not running anymore on iron dechlorination as major factor to degrade the contamination, but we switch to a biological treatment where the iron now becomes a catalyst in the treatment process. So what happens in, let's say, in reality, once the installation is performed, is that the bacteria that are introduced with the slurry and BOS 100 and the electron donor source are now starting to break down the starch into simpler molecules and simpler sugars, which allow the other bacteria, which are now those responsible of the ERD process, to be able to degrade the contamination. Any dissolved phase contamination traveling within the groundwater will still be absorbed onto the carbon. The difference is now that the bacteria present within the carbon structure, which are inoculated pre-injection, and the sugars that are being generated by the starch degradation, will now boost the treatment of the chlorinated compounds all the way down again to non-toxic gases. The only difference in terms of the dynamic process of the biological treatment is now that since a much higher amount of PCE can be treated and much faster by the biological process, we may experience, depending on the balance of soil contamination and groundwater flux, periods when DCE and vinyl chloride may be monitored within the groundwater, but this concentration will then disappear as soon as the mother product is completely removed from either soil or groundwater. The advantage, one little advantage of having starch as an electron donor source, is that starch has a very low solubility in groundwater. So once installed, this allows us to have a long-term source of electron donor to provide the ERD process with to maintain longevity for the ERD process. It's not just about the product that we install, but it's also about how we inject the product. So one, let's say, one important thing to mention about the RPI group is that we truly work on ensuring that the installation process is performed at the best way possible. So over the years, we have, let's say, made sure that we just don't work with simple equipment, but we are sort of custom built our own equipment to make sure that we don't let the geology drive where our injectates are, let's say, go or where they end up in the formation, but we truly force the geology to accept our slurry where we need it. So the first feature of our installation technique is that to work on a triangular grid, which can vary between generally 1.5 meter to, let's say, 2.3, 2.5 meter, depending on the depth of the contamination to be treated. Injections are top down, every 0.5 meter or 60 centimeters. The working pressure that we operate at can be up to 90 bar. That's pretty much the system pressure that we are able to deliver, which with flows up to 260 liters per minute. The reason why we want to work with high pressure and high flow is pretty much for two reasons. Generally, we know that contamination gets absorbed to, let's say, low permeability soils such silts and clay. And we need pressure to make sure that we create microfractures within these soils in order to distribute the product the best way possible. When it comes to more permeable soils, such as sandy soils and gravelly soil, we need flow for another reason. This is to allow us to distribute our product more in a turbulent way. Because if we work with low flow, what would happen is that this granulated carbon would be just filtered out by the formation. But by having a lot of flow and a lot of pressure behind our back, we are able to actually create a turbulent mixing without the formation. And another small feature, but important feature to make sure that we distribute the product the best way possible is to allow all the product to go from the mixing tank to the injection nozzle without any loss. And this is done by having hydraulic injection hoses going all the way from the pump to the nozzles, as we can kind of see in this little clip showing the tracks of high pressure, high flow. As mentioned, the reason why we do so, and it's a very important thing, is to truly fight the formation. And as we can see from this last drawing before moving forward, is to allow an homogeneous, as much as possible, homogeneous distribution across potentially different geological layers. How do we keep track on when we are in the field about the distribution, and how we try to make sure that we achieve the best distribution is by following pressure, flow, and exit velocity. We have our, let's say, call it intellectual property on how to make sure that this is done the best way possible. Control injection volumes for each interval, and this allows us to ensure that distribution is as best as possible, both between sand or clay formations. Here are just a few pictures to kind of show different cores that have been taken at different sites, both US and Europe, in different geological formation. The top left, we can see a typical kind of sandy distribution. This picture that we see in the bottom left corner is actually a picture from the site that we are presenting today, within the silty formation where most of the contamination was present. And the last picture is actually an interesting core, because it's a core that shows a sort of shift in geology from a more gravelly formation, where we can see a more, let's say, homogeneous distribution of the product, shifting to a clay layer where we can see this sort of micro roots where the product is distributed. Back to our project, back to our site. Now we are going to move into the sort of data that have been generated since the end of the injection. The first slide that we are going to be presenting is related to the PCE plume that was present in 2017 May, before the beginning of the injections, and the conditions that have been that are present at the last monitoring round that has been performed just a few weeks ago. As we can see, we can we notice a sort of implosion of the source area and a reduction in the concentration at the site boundary, which is the most important objective for the client. The goal is to bring the PCE levels at around 10 microgram per liter at the site boundary, which is located roughly where I'm pointing my mouse. And this groundwater control monitoring program for the time being is planned to continue until Q2 of 2022, so about a year from now. After this period, the client will go back to the authorities and discuss if there is any need to do more, or if the activities performed and the data provided are sufficient to claim a sort of closure of the site. The next slide shows us instead the conditions of the ethylene that have developed from pre-injection to post-injection. In this case, the reason why we started looking at July 2017 is simply because in May 17, there was absolutely no ethylene detected, so this map would have been just blank. So we just put something that shows the initial, let's say, effects of the injections. And here we can see the effect of the treatment in terms of ethylene generation in March 2021. What we notice already from this slide, and we will discuss more in the upcoming slides, is the effect, as we discussed, of the starch, of the electron donor slowly dissolving into groundwater and start to travel in terms of the sugars that are being generated traveling along with the groundwater flux. What's interesting about this picture is that, as we can see, we have a high ethylene generation downstream of the injection area. What this trigger, and it's something that then Mike will present at the end of this package, is the fact that we, when we started to see full conversion of PCE also further away from the injection area, we wanted to figure out what is that caused that. And that led us to perform some microbial analysis, which, as I mentioned, will be presented later by Mike. Just one short comment. What we are going to do now is also we are going to look into the source area by looking at data from 2 wells within the source area, X002 and MW27. We will then look at data from the transect directly downstream of the source area, MW63, 64, and 65, and then moving to another transect created by MW33B and MW9 at the site boundary. So starting from the source area, the data that we want to present is the actual evidence of DNAPL degradation thanks to the CAT 100 injection. Here we have a picture of the soil core that were taken at this location during the RDC. What's interesting about this picture is that we can see how like PCE would just flow in the gap where the soil was taken out of the core, showing the large amount of the DNAPL present. And this is backed up by 2 pretty much data: the soil concentration found in soil, which were up to 50-60,000 milligram per kilo, and the levels of DNAPL measured in the monitoring well that was installed in the same location. This graph shows us the trends of DNAPL measured by the consultant in charge of the monitoring at the site. And as we can see, since injections were completed, the DNAPL thickness and volume removed during purging activities started to decrease constantly until the last monitoring event that we have available in mid-March, where no DNAPL was either measured or observed during purging activities. To back up this, the additional line of evidence that we have to back up the removal and degradation of the PCE present in the source area is the data from the groundwater at MW27, where we can see the generation of acetate as a line of evidence of the starch degradation to simpler sugars, ethylene generation out of the full complete conversion of PCE, together with the chloride generation. And as we can see, as soon injections were completed in August of 17, we have a sharp increase of all these compounds. X002 is a well that is extremely close to MW27. And as we can see as well from the data taken from the consultant in terms of groundwater, we can see as well here the sharp degradation of reduction of PCE in groundwater, followed by a temporary increase of TCE, followed by some up and downs again in DCE, and very little presence of vinyl chloride. But again, when we look at the biological activity data, we can see the increase in ethylene and chloride concentration, which is a clear indication of full conversion being achieved. Moving on to the next transect present on that we want to analyze or we want to look at in terms of data. We have 3 wells located downstream of the source area in the basement. And we can see in all 3 wells, MW63, MW64, and MW65, how the PCE concentration have been clearly brought down to, in pretty much all cases, to non-detect almost levels. And the clear kind of evidence of the ERD process, where we have a nice decrease in PCE concentration, followed by a spike in TCE, followed by a spike in DCE. In this case, no evidence of vinyl chloride. We only present the MW66 data, 65 data in terms of biological activity, but as all the other wells, we notice an increase in ethylene and chloride as part of the full conversion. The difference between 63, 64, and 65 when it comes to current condition of DCE and vinyl chloride is simply the proximity and vicinity to the source area and the fact that we have still mass, PCE mass, that is being treated, hence generating some of these byproducts. The next transect that we are going to be looking at is the off-site sort of transect MW9B and MW33B. What we want to highlight out of this data is a simple fact, which is, as discussed, over time, based on the ethylene data, we noticed that we were sort of stimulating some full conversion of PCE at the site. What we can notice from this data is that when we look at the effect of the BOS 100 on the ERD process, is that once the sugars have reached the area of MW9, where only BOS 100 was installed, no CAT 100 in this case, we can see how the DCE and the vinyl chloride concentrations are sort of contained from going, let's say, too high. In the case of MW33, which in terms of baseline value had similar PCE concentration to those of MW9 at the beginning of the remediation, we can see that without the presence of BOS 100, we have a slightly different profile in terms of DCE and vinyl chloride concentration. What this slide wants to kind of tell us is simply that we are able, when we use the right, let's say, ingredients with our treatment, to make sure that we do not exceed potential levels, dangerous levels of DCE and vinyl chloride in critical locations. To start wrapping up, I just would like to kind of present a couple, I call them 2 eye candy slides, where Ejlskov has developed kind of in-house software which allows us to kind of perform and deliver to the client to the best detail possible, both the site investigation data in terms of RDC and post-remediation data. So the first slide wants to just show the plume development of PCE over time, and we can see as the time bar goes along the implosion of the source area, and at the same time the reduction of the PCE concentration along the site boundary. With the second slide, which will come up shortly after this, we will look at the same type of development, but in this case for the ethylene plume. And in this case as well, we can see how at some point in 2018, the sugar splitting out of the CAT 100 injection area started to stimulate a rapid conversion of PCE in the downstream areas all the way down to ethylene. And with this, I'm going to move to the next slide where Mike will kind of touch based on the microbial study that has been done at this site last year. Back to you, Mike.
Thank you, Giorgio. If you've got any questions, go ahead and start putting them in. This is the last slide here. So we'll go ahead and talk about some of the microbiological testing that was done. The one thing that I forgot to mention on the front end of this presentation, I was trying to kind of rush through the introduction to get to Giorgio's presentation, is Giorgio's joining us today from China. So he's in quite a different time zone than probably most of us. So I just wanted to say thank you to him for setting aside the time to present this today. So before we get to the questions, we wanted to, this site, Giorgio had kind of given a little bit of background on why the sampling was performed. And, here in the States, we use this microbiological testing kind of, we try to grab samples baseline and we can track it as we go through the project. On this particular site, we didn't have any sort of baseline samples or any baseline data. So these samples were collected quite a ways into the project, but we wanted to be able to back up what we were seeing with that ethylene generation that you see on this image that I pulled out of Giorgio's presentation. So 5 different samples were collected. You see the background sample up there in the upper right, and then we sort of worked our way down from the source area, X002, MW65, still in the source, but a little down gradient. MW9B, so that's the area where just the BOS 100 was applied, and then MW33B is down gradient of the cat area. So it's just capturing, it's getting some of those sugars to acetate that's kind of moving downstream of where the cat was injected. And so just a couple trends, again, we don't have anything to compare it to. There aren't any plans to go out and grab additional analyses, but a couple of things that we can pull out of the data. First, that DHC was not present in that X002 sample that we have up in the source. It was the only sample that did not have DHC out of the 5. We actually had some detections even in our background sample, and that's probably due to the DNAPL that's present. However, if you go back and remember, we are getting vinyl chloride generation as well as ethylene generation, so we are getting complete conversion. Now there are some Dihalobacter detections there in the 10 to the 3 range cells per mil, but we didn't see any functional genes, and we didn't see any DHC. Things changed quite a bit. The 3 wells that are downgrading, I tried to summarize those. DHC was present in all 3 of those. The max detection was 7.45 times 10 to the 4 cells per mil. And what was very interesting is that the genomic sequencing identified DHC. It was one of the top 3 species identified, from 11 to 71% of the population, as well as vinyl chloride functional genes were present in all 3 of those wells as well. And the one thing that you'll note down there, my last bullet in that bottom text box, is that DHC is not added with consortiums. And so using that background sample, we can tell that we can determine that there was some DHC present in that source area where we have DNAPL. Probably not, just because of the concentrations there, but it is present, and by the addition of the complex carbohydrates as part of the cat blend, the cat 100 blend, we're able to boost the DHC populations to be able to get complete conversion down to ethylene. So I think we'll wrap up there. Dwayne, if you want to come online as well, and we can go ahead and enter the Q&A portion.
Sure. So the first question, Mike, I know you've got to jump off here soon, but let's jump into this. First question is, can you go over the mechanisms to get complete conversion of the source mass?
Yeah, so can we go over the mechanisms to get complete conversion in the source area with no, it says FGA presence? So functional gene assay. Okay, so from the so Dwayne, from that, I would say that most of that biological, there is some biological activity taking place with the Dihalobacer present. However, it's we don't know, to be honest. I mean, we are getting some ethylene generation from the beta elimination pathway via the iron, but I would assume that there are some microbiological processes occurring there, even though we did not detect any DHC present. But again, this is only one sample in time, so it would be nice to have more samples in time to see if maybe DHC would be detected in that source area.
But Mike, I would add to that is that we know that there's extensive biological activity going on within the source area because the CO2 monitoring that we've been doing since baseline all the way for the last 2 years, and there's a significant amount of CO2 being generated within that source area. So there is biological activity going on.
Right.
And the CAT 100, you can't think of it just as an ERD process. It's a donor electron exchange, on the iron surface itself. So it's not a typical ERD, process. That's the power of the CAT 100 with the catalytic, reaction occurring on the iron itself.
Okay, well, Dwayne, we can toss this one to Giorgio, and then I'm gonna have to jump off here. But one question for you, Giorgio: did you have any depth limitations using the MIP in the till?
Pretty much, we always got to bedrock. I was personally there during the MIP when we did the RDC, and we always reached bedrock in any single location without any issue. The area downstream of the building was definitely more tough to get through, and we had also been noticing how uneven the bedrock was because we personally lost a probe at some 25 meter, not because the probe was 25 meter deep, but because it just kept sliding on some very uneven bedrock. So we no problem at all.
All right, Giorgio, another question, which you and I can both, talk about this. Why are DHC not added with CAT 100 consortium? And I guess the point is that what we've learned is the DHC don't really want to, play in the same sandbox as a lot of the other consortium that we have with CAT 100. There's a large amount of bacteria that are added just for the breakdown of the starch alone, in order to generate fermentation and generated the acetate to support the CAT 100 process. There are dechlorinators that are included as a part of that blend, but they do not include the DHC. But like Mike said, not just this site, but many of the sites that we've monitored where CAT 100 have been applied, and some of those have been in the ground now for 5 years, that baseline DHC, there's low levels of DHC present at a majority of these sites, and then the long-term monitoring, the CAT 100 installation has actually stimulated those DHCs to, you know, healthy consortiums for reductive processes, you know, to the +4, +5, +6 range, you know, cell counts per milliliter, to where they've been sustained on the one site, the longest running CAT 100 site in Evansville, Indiana, where, you know, those cell counts have been up in that zone for now over 4 years and continuing to generate, you know, the healthy environment that you want to see from you know, for the cell counts in order to be, you know, I guess a powerful reductive process. Another question, I guess that's kind of answered that same question. Where other microbes introduced with the CAT 100? If so, did they flourish? I guess the answer is yes, they are flourishing based upon, you know, the monitoring that's being performed. Like I said, you know, we, in addition to, you know, just monitoring VOCs, we're also looking at, you know, dissolved gases, RSK 175, 13 different dissolved gases. We're also looking at CO2, and we can see that in addition to the microbial analysis, that there's all lines of evidence that the consortium is thriving, not only just in the degradation of the mass itself, but all the other signatures that give us indication that everything is healthy. Any estimate of the groundwater velocity in plume strata? Giorgio, you got it?
Well, that one, I think there were some old investigations done in the early 2000s, but let's say that for our purpose of the remediation, we didn't really do any specific calculation, but we could kind of estimate now based on the moment that this full conversion has started to occur between the injection area and the downstream well. So we had a period of about a year between the time the injections were completed and up until the first kind of full conversion signs were seen some 40-50 meters downstream of the injection area. So one could say that you are looking at roughly 40-50 meters a year in terms of let's say groundwater flux velocity. If it is based on what we know from the sampling, is also a very fast recharging formation. When we did soil sampling, we had floating sands in some areas of the site, so we know there is a lot of saturation, like the soil is really saturated down there.
All right, Giorgio, one question popped up. You know, you had indicated that the PRB was the original plan for the remedial strategy for the site. And then once the RDC identified the significant mass, then that plan changed. Was there still a PRB that you all had provided as a part of the overall strategy?
Throughout the negotiations with the client after the RDC, there was a possibility of having the PRB as a sort of backup plan down in time, so to speak. At the time of the RDC completion, shifting to the remediation, the client had a specific budget available for the remediation, and coincidentally, the initially estimated price for the PRD equaled the price of the installation that we performed in 17. We know now, and we are quite confident now, that the efficiency of what we have done in 2017 with the source treatment compared of the results we may have been seeing at this stage with a simple PRB would have been completely different. So that's as we said, the client is planning next year to revise a sort of a new risk assessment towards the authorities based on the data that will be available at Q2. Based on that, there will be a time for decision in terms of what to do next, if it's monitoring the way forward to continue with that, or stop monitoring, or will the authorities need further remedial activities. That's to be seen.
Well, I guess we can share that data a year from now, where we stand at that point in time. But if it continues to progress, then hopefully they're going to be able to get a managed closure of some sort. Yes. Well, I'm going to wrap up, Giorgio. I do appreciate, Mike said, I do appreciate you sharing your time with us. I know it's late in China, and take care of yourself. Take care of yourself. Yes. I appreciate everybody joining us. Hopefully, if you have additional questions related to this site, you can always send emails to Mike Mazzarese or myself, Dwayne Guilfoyle, and we can get Giorgio involved. There is a lot of data that's beyond this. Giorgio summarized a whole lot of data that's been collected over the last 2 to 3 years. And I'm sure that we can get into more in-depth conversations related to the mechanisms associated with Cat 100 and the processes that are going on at the site. And we can also provide additional information, even microbial data for other sites that we have more than one event where microbial analysis has been collected over a 4 to 5 year period of time. But with that, I'm going to sign off, and I appreciate everybody joining us. Hopefully you can join us again next month, where we get into more in depth on the qHRSC program, which kind of summarized here on this site that Giorgio performed and how it plays an integral role in predictions of performance and hopefully optimizing the remediation cost for sites. Thank you.
Thank you, everybody.